So I wanted to do a follow-up of the rubbish pink power bank for two reasons. The first is that I wanted to find out what was going on when the boost converter in here, about 10 minutes into the video test, was dropping to 3 volts intermittently, and I'd like to see when that happens. I suspect it's to do with the voltage out of the battery at a under high load, but I'll see if we can reproduce that. And the other thing I wanted to do is find out what capacity the cell within it is. Now, in order to do that, I've charged it up in an external charger. It's charge finished, so this should be at 4.2 volts. And let's test that. With the multimeter. You can see that. So just for the sake of completeness, 4.16 is currently reading. There we go. Or 4.17 if you round it up. So what I intend to do is hook this cell of unknown capacity up to this little load here, which is actually very good. It's made by a guy called Jasper in the Netherlands. He sells them on a site called Tindy, and it's a little programmable electronic load, and it's the interface to it is via a little Arduino clone, which is hooked up to the computer, and it measures voltage and current at the same time. It also keeps track of the milliampere hours provided, and it is happy at proper voltages rather than just USB like a lot of my other little testers. So I'm going to hook this battery up, and then we're going to see what a little bit more wire. Not got a great deal actually. Hook straight onto there. Yeah, let's do that. That avoids this horrible crappy little wire from getting in the way as well. Let's get this tape off. I do wonder whether this wire might be part of the problem, because it's very thin, and I do wonder if the actual voltage drop when we were pulling a full amp is the reason why we weren't getting a very good result in the discharge test. So let's rest that there. Now you won't be able to see this, but on the load, which I am just about to start recording the video for, so that's currently reporting 4.161 volts, which is, let's compare that for the sake of accuracy. .16. So this is going to be a fairly boring part of the video, so I'll start this off and then move on to something else. So this little load, one of the things you can do is tell it, you can limit the cutoff voltage, which I'm about to do. So S for status, so you can see where are we, voltage 4.16. This is the start time. It's been on for a little while, and this is the help page. So what we're going to do is set the voltage limit at 3 volts, which is 3000 millivolts in this interface. And then I'm going to set the in constant current mode, and I'm going to draw an amp from this battery. One second. Okay, I've just enabled the log as well, so we can do something meaningful with the figures outputs. So, once again, if I just run the status command, you can see all the figures are zeroed, but for the sake of argument, reset the counters, and then we start the constant current mode at 1 amp now. And there it goes. So while that's running, let's move on to testing the boost converter. Let's get rid of that. So in order to test this, I'm going to be using bench power supply, angle this so you can see, and these crocodile clips are hooked up to channel 2. So just to focus on that. There we go. So set those up, and I'm going to be using the standard USB load for this. So we're going to arrange this so you can see. Needs to be that way up. That did not go well. Replace my fill light. So if I turn the power supply on, so adjust the focus slightly. There we go. So if I turn the power supply on, working? Not obviously. 4.2 volts. Oh, not a resounding success. Output is definitely turned on. Check what the multimeter says. Yep, 4.2 volts. That might be why. I needed to turn the dials down. Okay. Let's turn that back on. There we go. Right, my apologies for being a bit useless there. You can't really make that out at this angle. So, the USB boost converter is outputting 5.2 volts, 0 amps. So we'll turn this up to 1 amp, which is what we did last time. with the... Yeah, that looks good. So at 1 amp, this is still outputting 5.2 volts, which is consistent with what we saw last time. The bench power supply, we can see, is outputting 4.2 volts, drawing 1.5 amps, which is reasonable. That's for the stepping up of the voltage, you'd expect there to be an increase in the ampage. Now, trying to draw 1.5 amps through these little cables, my guess is that they're not particularly good for high current draw, and I suspect that as the battery voltage drops, the current has to increase because we need to keep the voltage at 5 volts. What I suspect is over the length of these cables, and they were, I don't know, maybe probably 110 centimetres, 3 inches long, the voltage drop across them under current, certainly approaching 2 amps as the battery voltage drops off, is what would cause this to drop out, but let's find out. So if we start to drop the voltage, we should see a corresponding increase in the amps, so 1.56 at 4.1 volts, 1.61 at 4 volts, still nice and consistent, 5.2 volts, so 3.9, 1.6 amps, 1.73 at 3.8. So 3.7 is sort of the average output of a lithium-ion cell. So it's drawing nearly 2 amps down those tiny little cables at this point. They might be rated for 2 amps. Doubt it. So if we drop this lower, what point does the boost converter start to flicker on and off? 0.92. Still consistent at 3.5 volts. There we go. So if I turn this back up, interesting. Oh, it's capped at 2 amps. My bad. Well, that has upset it, which is not a massive surprise. Let's unplug this and start again. Oh, it's actually quite warm. Let's turn the power off. Reset this. Power back on. Let's turn everything off and back on again. There we go. So if I run this back up to 1 amp, so 3.6 volts drawing 1.97 amps, so if I drop this another block, 3.5 volts, 2.06 amps, 3.4 volts, so as long as the battery can supply over 2 amps, the boost converter seems to be doing okay. 2.25 amps at 3.3 volts. So this is quite impressive. So it's only as the... oh, there we go. So it's powered off at 3.2, 3. So that may actually be the cut-off voltage of the battery protection circuitry. Okay, that is quite warm now. Okay, let's reset that. on. Let's back that off a little bit. Yeah, that's actually not very happy. Well, this is exciting. So that's actually very warm. I think the moral of the story is that running this at a full amp is too much for it. I think either some thermal cutoff has kicked in, or I've killed it. No, it's still alive. So 3.2 volts. Let's go back to an amp. It's still working. So if we dial this down a tiny bit at a time, 3.19, 3.18, 3.17, 16, 15, 14, 13. There we go. So that seems to have cut itself off nice and cleanly. But that is assuming that the power supply is capable of delivering a nice consistent amount of current, and I think this battery is not. So what's happened is as the battery empties out, not only is it no longer capable of, the boost converter will work at whatever voltage it seems, but it's no longer capable of supplying the current required. So what we'll do is turn this back up to something reasonable, 3.3 volts. We'll plug this in. No. Let's turn the power off to it and back on again. Okay, that's better. So still doing an amp. And then we'll start to drop the current slightly. So it's currently drawing 2.26 amps. So back it down to 2.3. And then if we start to reduce the current, there we go. So as soon as the voltage drop happens, so this is interesting. If I turn that back up a bit. So it seems to get itself in a bit of a state. As soon as it's capable of, as soon as the voltage is recovered, the boost converter doesn't. Sorry, as soon as the current is recovered, the boost converter doesn't. Wow, that is really hot now, which probably isn't helping. Probably have to turn the voltage up a bit, but let's not do that. Probably if I turned the power off, wouldn't it? reset that. There we go. So last time I think. 1 amp, 5.2 volts still. It's very consistent. So it's drawing 2.23 at the moment. So if we back that down slightly. It's still doing okay. Oh. So it starts to make a noise at that point. Oh, it's making a lot of noise. And if I turn the current up, yeah, it just turns itself off. So it looks like what's happening was that as the draw through the battery was getting beyond what it could deliver, the boost converter, well, it's not clear what was happening there actually, because when it was pulsing on and off in the original test, we were seeing it recovering to 5 volts, and it's not doing that here. Now it might be that when it's dropping off and it's on a battery rather than a tightly controlled load, it's capable of drawing enough burst current to fix itself, but without fiddling too much more, it's not going to be easy to reproduce that. So yeah, on the whole, I think the conclusion has to be that this is never going to work reliably at 1 amp. These cables, now I've opened it up, these cables are just not beefy enough to consistently do, or if they were, somebody's significantly cheaped out. Drawing close to 3 amps through tiny little cables like that is always going to lead to a significant amount of loss in the wiring, and a lot of these solder joints aren't brilliant either. That probably doesn't make too much difference, but interesting nonetheless. So the final remaining thing to do is, if we go back to here, you can see the LED is still flashing, so we're still discharging. Looking at the output, the battery's currently at 3.8 volts, so it's about just over halfway discharged. So what I'm going to do is leave it running, and then come back when it's run out. Right, that's it at 3 volts. It's delivering less than 0.2 amps now, so I'm going to stop the test. And the status, there we go, so 2062 milliamp hours, current voltage 3.012 volts. So it's just over 2000 milliamp hours, this cell. And if we compare that to the readings we had, so when we did the test on USB, the pink power bank came in at 1162 milliamp per hours, which, oops, if we do this on the calculator, 1162 times by 5 gives us 5,810 milliwatt hours, This battery's just come in at 7,269. So if we divide that by 7,269 times by 100 gives us 79.9% efficiency. So this little boost converter attached to that cell appears to be just under 80% efficient. So there we go, good to know. Looks like it's about a 2000 milliampere hour cell, so curiosity satisfied. Just trying a new microphone arrangement for this final part of the video, so it'll be interesting to see whether it sounds better. The only remaining thing to cover is the discharge curve using the data output by the load. I've plotted that into a spreadsheet, and you can see that from the beginning it dropped from just over 4 volts. There's a slightly squashed version of the standard lithium-ion discharge curve, but it looks like the normal one, and you can see that it discharges reasonably consistently. It's delivering an amp right up until the point where it hits 3 volts, at which point the amount of power it can deliver drops off quite dramatically. So that's a great example of why you should never discharge a lithium-ion battery below 3 volts. But it's an interesting use of the data that we get out of that little load. So I've included a link in the description below to that load and the guy who makes it. It's quite neat. It's nice that you can calibrate it if you've got a reasonable power supply and multimeter, which is also handy. Thank you for watching. Please subscribe if you're interested in more testing.